In this lesson, we'll be learning about some of the special properties of water. So, first of all, why do we care so much about water? Well, about 60 to 70% of the human body is water. And you can see a list of the different functions that water performs that helps to keep us alive. If you're ever kind of stuck out in the wilderness, it's much more important to find water compared to food. You can live for weeks or even months without food, but you can only live maybe a couple days without water. So, looking at some of these functions, we can see that it helps to kind of moisten the tissues of your mouth, eyes, and nose. It helps to protect your body organs. So, you actually have kind of sacs of fluid that surround your internal organs, like your heart and lungs. And these sacs of fluid help to kind of contain infection. It also helps to reduce friction between the organs. So think about your heart beating and your lungs inflating and deflating, and they're right next to each other. And if they were to rub against each other, that would cause friction. And friction causes heat production. It also causes wear and tear. So think about if you've ever had a blister, you know what happens when there's friction between your skin and your shoe, for example. We also need water in order to get rid of waste products. So here it says that it helps to prevent constipation, but it really helps to carry waste products out of the body. And that's also reflected here by the need for water for the kidneys. So the kidneys especially help to flush out waste products as well. Water, there's also a lot of water in our blood and the extracellular fluids surrounding our cells. And these fluids help to transport materials throughout the body. So the primary function of your blood is to transport material from one spot to another. And that material can include anything from hormones and nutrients to respiratory gases like oxygen and carbon dioxide, as well as vitamins and just all of these things that all of your cells need in order to survive. Water is also really good at helping us to regulate our body temperature. So think about sweating. When you sweat, that's one way that your body can physically remove heat from inside your body and get it out of your body into the surrounding environment. It also helps to transport heat around all the parts of your body. So think about your blood. It's not only transporting nutrients, it's also transporting heat from one place to another. Water helps to lubricate our joints. Synovial joints are you might be familiar with them as your freely movable joints. So these are like your shoulders, your elbows, your knees, your ankles, your hips, your wrists. These are all of your synovial joints. And these synovial joints have their own little kind of a pocket or a collection of fluid around them. And that fluid kind of acts like an oil. It helps to protect the end of the bone so that when they're moving, they're not rubbing against each other. Because once again, friction can cause heat production, but also wear and tear. And over time, as we get older, our body is not as good at making the synovial fluid, and our cartilage starts to wear down, and that's actually what leads to osteoarthritis. So that's kind of an example of what happens when there isn't enough water or it's not in the right spot in our body. And then as we mentioned down here, the blood helps to carry nutrients and oxygen and other stuff around our body. Now, water is a polar molecule, and this polarity gives it a lot of kind of special properties. But first of all, let's do a quick review or reminder of what it means to be a polar molecule. So the chemical formula of water is H2O. So we know that means that there are 2 hydrogens and 1 oxygen making up a molecule of water. And we can see our pictures down here. We can see how the water is an oxygen bonded to these 2 hydrogens. And it looks kind of like an upside down Mickey Mouse. Now, the bonds in between the hydrogens and the oxygen, so this bond here and this bond here, these are covalent bonds. And remember that in covalent bonds, the atoms share electrons. All right, so these are pretty strong bonds. However, they don't always share these electrons equally. So you can see in our little diagram here that oxygen has a partial negative charge. And that's because oxygen actually, the electrons that it shares, it actually keeps those electrons more than it shares it with hydrogen. And remember, electrons are negatively charged. So if the electrons are spending more time with oxygen, it's going to give oxygen a partial negative charge. The hydrogens are losing those electrons at least part of the time to oxygen, so they end up with a partial positive charge. And so this kind of the negative end and the positive end, this is what we call polarity. And if you think of a battery, so batteries, like a AA battery that you put in something, it has a negative end and a positive end. And so batteries are polarized or they're charged. And so that's kind of one way to kind of think of it. Now with water's polarity, remember we have these kind of Mickey Mouse looking molecules here. And the oxygen has a partial negative charge to it. And the hydrogens have these partial positive charges. And we know that when it comes to charges, just like with magnets, opposites attract. So the negative side of oxygen is attracted to the positive part of hydrogen. So there's actually an attraction that happens here. And it's kind of like a magnet holding these molecules together. And remember that this attraction here is called a hydrogen bond. Now we're going to focus kind of on water's polarity and its ability to form these hydrogen bonds because it gives water a lot of special properties that helps it to sustain life. So here's a list of some of water's special properties, and we're going to go over these in more detail in the following slide. So first of all, water is cohesive, or it has this property of cohesion. And what this means is that molecules of water stick to other molecules of water. And once again, that's just due to that kind of partial negative and partial positive charges forming those hydrogen bonds right here. Okay, so that's cohesion. And that gives us this concept known as surface tension. And surface tension is illustrated in this picture here. So this is a little water strider bug. And I've also heard them called Jesus bugs because they can walk on water. And so you can see this bug, you can actually see that it has these little indentations in the kind of in the water where the weight of the insect is putting a little bit of pressure on those hydrogen bonds, but it's not heavy enough to actually break the hydrogen bonds. And so for something that's lightweight, like this water strider bug, it can walk on water without a problem. Now, these hydrogen bonds aren't super strong. They're actually pretty weak bonds. So that's why if a human tries to walk on water, we just sink right through. But that's because we're too heavy and we break those hydrogen bonds. Now, a similar concept is this concept of adhesion. And adhesion just means that water sticks to other molecules, especially molecules that have a charge to them, or even if it's a partial charge or a full charge. And this property gives us something called capillary action. So if you see this kind of picture here, you can see that if you were to put a tube, we call these capillary tubes, and they're just kind of a thin, usually made of glass or plastic tube. And you see that if we put the tube into a beaker of water, the water actually starts to climb up the tube and actually climbs up above the water level. And that's because the water molecules that are down here, let me switch to a better color. The water molecules that are down here are attracted to little partial charges in the kind of the wall of the glass tube. And that allows the water to actually climb up the inside of the tube. Now, once again, there's a little bit of limitation to this because these hydrogen bonds are not very strong. And so if the water were to try to go higher and higher, gravity would break those hydrogen bonds and send it back down. But we can get a little bit of that capillary action there. And remember, these properties are due to that polarity. So this is kind of the word of the day is polarity. And it's because those opposites attract. So it just means that when you've got your negative charge with your positive charges, it means that the negative is going to be attracted to the positive. And that's that hydrogen bond attracting there. All right, so opposites attract, polarity, hydrogen bonds. These are all associated with these concepts of cohesion and adhesion. Now, water is also a really good solvent. Not everything dissolves in water, but a lot of stuff does. Now, water is a polar molecule, and it can dissolve other polar molecules. So there's kind of a saying in chemistry that like dissolves like. And what that means is that, let me finish writing this. What that means is that water is a polar molecule, and it can dissolve other polar molecules, whereas something like oil is nonpolar, and so nonpolar molecules can dissolve in something like oil, but not in water. Now we can look at these terms of hydrophilic and hydrophobic, and these are terms based on how likely a molecule is going to interact with water or not. Now, if we look at the word hydrophilic, we can kind of break it down into two parts. So there's hydro and there's philic. And hydro means water. You should think of hydration, hydrogen. And philic means love or to like something. So the term hydrophilic actually translates to water loving. And so something that is hydrophilic is going to either readily interact with water or dissolve in water. So think about like sugar. If you add sugar to water, it dissolves. Sugar is a polar molecule. If you add salt to water, it dissolves. It has some polarity to it. It has some charges. If you try to use a paper towel to wipe up water and it absorbs it and soaks it up, it's because the molecules in the paper towel have some polarity to it. Now, hydrophobic substances, if we look at that kind of that suffix of phobic, a phobia means that you're afraid of something or that you are trying to avoid it. And so substances that are hydrophobic are things that do not dissolve or interact with water. So if we look at the examples over here, we can see like a piece of water laying on a layer of glass here. Water doesn't absorb into glass, and that's because glass is nonpolar and it's hydrophobic. If we look at mixing oil with water, we know that oil and water don't mix, and the oil globules kind of stay together, but they don't mix with the water. And so that's an example of what a hydrophobic molecule or substance is. When we discussed bonding properties, so when we discussed covalent bonds and ionic bonds, we talked a little bit about how water can basically break apart the ions that make up an ionic compound. So remember, we looked at how sodium and chlorine, remember that sodium gives chlorine an electron, and because they have those opposite charges and opposites attract, they kind of hang out together and they form that ionic bond. But remember that water also has some partial charges to it. And so the negatively charged oxygen is attracted to the positively charged sodium, and the positively charged hydrogen is attracted to the negatively charged chloride. And so water actually has the ability to break this ionic bond. And in doing so, when, for example, when sodium and chlorine separate, the chlorine keeps the electron that sodium gave it. And so we end up with these ions of sodium and chlorine, or what is also called a chloride ion. So ionic compounds dissociate in water. So we don't really use the word dissolve, we use the word dissociate because they are no longer associated with each other. Now these dissociated ions, when they are dissolved in water, so basically ions in water, and I just said the word dissolved, but I should have said dissociated. So when ions dissociate in water, it forms these things called electrolytes. And you're probably most familiar with electrolytes because of sports drinks like Gatorade and Powerade, because these drinks have ions in them. And so it's essentially salt water. But it's not just sodium chloride. It can also be other charged particles. So electrolytes, some common electrolytes include sodium and the chlorine, but we can also get potassium, calcium, magnesium, and some others. So the next time you're drinking a Gatorade or some sort of kind of sport drink, look at the label and see which of these electrolytes you can recognize on the label. Now, these electrolytes help certain things to happen in our body. So some pretty common examples that if you take anatomy and physiology, you'll learn more about how these ions are involved in muscle contractions and nerve impulses. And just to give you a preview, in order for these to happen, you need to have sodium, potassium, and calcium. So these are really important for these processes to happen. Now, you may be familiar with the three main forms of matter. And so the three main forms of matter are that matter exists in either a solid, as a liquid, or as a gas. And so when we look at water, the difference between these, because regardless of whether we're talking about liquid water, water vapor, which is the gas, or ice, which is the solid form, it's still all H2O. So it's the same molecule. The difference is what is happening with those hydrogen bonds between the atoms. And so remember, we've got our kind of partial charges, and we have this kind of hydrogen bond connection between these opposite charges. And so that's the H bond there. Now in ice, what kind of makes ice special, or what makes water form this kind of solid crystal, is that these hydrogen bonds between the water molecules form and they become a little bit stronger, a little bit more stable. And so ice kind of takes on this hexagonal kind of six-sided molecule here, or I shouldn't say molecule, but structure. And this forms these kind of crystals of ice. Now in liquid water, we still have those hydrogen bonds. It's just that they are not as strong. And so they're constantly forming and breaking. And so you can see here that there are some hydrogens that are here, or some hydrogen bonds, but there are other hydrogen bonds that are not forming between each other. And so basically for every hydrogen bond that's formed, another one is broken. And that's what keeps water as a liquid. Now as a gas, the heat breaks up the hydrogen bonds in between these molecules of water. So there's no hydrogen bonds. And this lack of hydrogen bonds makes these molecules separate from each other, and then they can go into the air as steam. And I just realized, as I'm looking really closely at this graphic right here, that the hydrogens and the oxygens are in the wrong spot. Because remember, the oxygen is supposed to be here, and the hydrogen is supposed to be here. So I'm going to have to fix that in the future. But for now, the concept still applies with regards to the formation and breaking of these hydrogen bonds. So really the only difference between these concepts here is the stability of the hydrogen bonds. One really cool property of water is that the solid form of water floats in the liquid form. And this is kind of unusual when it comes to other substances in chemistry. Most other chemicals, when they are solid, they are denser than when they're liquid. And something that's denser is more likely to sink. But the key thing with water is that ice floats. And this is really important because it helps to keep bodies of water from freezing solid. And this actually insulates the stuff underneath so that it can survive. So let's move on to the next slide, and I'm going to show you, kind of draw out a little example of what I mean by this. So imagine that there is a lake. All right. All right, and in this lake you've got fish and maybe some plants. Now, let's say it gets cold, and so the temperature drops and it gets really cold. Ice would start to form on the surface of the water. Now, if ice did not float, what would happen is that this ice would actually fall down to the bottom of the lake. And what would ultimately happen is that the ice would keep forming up at the top and then sinking down to the bottom. And ultimately what would happen is that the lake or the body of water would freeze from the bottom up. And so you would end up with a solid block of ice or a solid kind of frozen lake here. Now, if you're a fish, that means that you are now dead. All right, so if you were a fish, now you are frozen solid and you are dead. But let's take a look at what really happens. So now we have our same lake. We've got our little fishies in the lake and our plants. And in reality, what really happens is that ice starts to form at the top of the lake. But as it forms, it stays at the top of the lake because the ice floats. And so what happens is that it actually forms a layer of insulation. And so regardless of how cold it gets out here, it's going to stay liquid down here for a while. Now eventually this ice can get thicker and thicker, but it would take it a really long time to get to the point where it was frozen solid. And this is kind of if you think about people that go ice fishing, they can actually cut a hole in the ice, and then they can stand on the ice with their fishing pole, and they can actually fish for the live fish under the water, even when it's really cold. And when I lived in upstate New York when I went to college, and it was really cold there in the wintertime, and I actually went out to a lake one time that had frozen solid, it had not frozen solid, but it had frozen along the top, just like this example here. And so my friend and I actually went out and we were walking on the frozen lake because that was really neat to us. And there were some guys out there that were ice fishing. And so one of us kind of showed us how he drilled through the water and was able to put his hook down into the water to catch the fish. Now, on a similar note, water has a high specific heat capacity. And the formal scientific definition of heat capacity or specific heat is the amount of heat 1 gram of a substance must absorb or lose to change its temperature by 1 degree Celsius. And so that's kind of, the fancy scientific version of the definition. But what that really boils down to is that water has a really high specific heat. It actually has the highest specific heat capacity of any liquid. And so the takeaway point is this. It takes a long time for water to heat up and to cool down. And so, if you think about it, if you've ever tried to boil water, you know that it takes a while for the heat to change the water from a liquid to a gas. If you've ever tried to freeze water to make ice, it doesn't happen super quickly. It takes a while for that to happen. And that's because it takes a lot of heat, either going in or coming out, in order to really change the temperature of water. Now, it's a pain when we're trying to boil water to make mac and cheese, or if we're trying to make ice before we have a party or something. But this is actually a really, really helpful property of water because, for one, it helps to keep the earth from basically freezing every winter and boiling every summer. It helps to kind of moderate the temperature of the climate on Earth. And if you go to other planets that don't have water, their temperature range within a single day could be a difference of hundreds or maybe even thousands of degrees. Whereas here on Earth, a typical swing in temperature from day to day is it might be tens of degrees. And, in some extreme cases, it can be really cold some areas and really hot some areas. But it doesn't get into the, hundreds of degrees that the temperature is changing from day to day. If we had those drastic changes, it would result in life as we know it dying. There's only a small handful of organisms that can survive in really, really high temperatures or really, really low temperatures. And humans are not one of those organisms unless we use technology. Another thing that specific heat capacity does is it helps us to maintain a normal body temperature. So it helps to distribute heat around our body. It also helps us to get rid of heat when we're too hot, but also hold on to heat when we're starting to get too cold. If it weren't for water, let's say we had a different liquid that made up the fluid in our body and our blood. So let's say instead of water, we had alcohol or oil as the main fluid in our body. What would happen is that when you walked outside, in the summer in Phoenix and it's 120 degrees, your body would heat up to 120 degrees a lot faster and you would die a lot faster. Even with water, you can't stay out in 120 degree weather without having, water or shade or some way to cool yourself down for very long, or else you can die. But if our body fluids were something other than water, you would die a lot quicker. So that's kind of a helpful thing about water. So kind of going along with water's high specific heat capacity is water's high heat of vaporization. And this is the amount of energy required to change 1 gram of a liquid substance to a gas. And so basically to switch liquid water to steam or water vapor. And this concept really comes into play when it comes to sweat. And so you can see this picture here with the sweat. Sweat is a really good way to get heat out of our body because these droplets of water are actually pulling heat out of the body, and then that heat is dissipating into the environment. And if you've ever seen someone, usually like an athlete, let's say like a football player, and it's cold outside and they're playing in the Super Bowl or something, and they go to the sideline and they take their helmet off, and you can actually see steam rising up off of their head. And that's because they've worked up a sweat because they're working really hard out in the field. And when they take that helmet off, the sweat that has formed is going to start going up into the air, and it's going to take the heat with it. This is another reason why if you've ever kind of hung out really close to somebody, you can actually feel the heat radiating off of their skin, and it's because of this sweat. Now, if water had a lower heat of vaporization, it would evaporate quicker and not take as much heat with it. And so we would actually have to take in a lot more fluid. But this high heat of vaporization means that we still need to drink a lot of water, but we would have to drink copious amounts more if our body fluids were something other than water. Also, I just want to point out this term of evaporative cooling. And this is the concept of sweat removing heat from the body. So when it evaporates, And evaporation is just when you have the water change from a liquid to a gas. So remember, evaporation is just something changing from a liquid to a gas. And so this evaporative cooling is just the sweat changing from that liquid form of the sweat into the vapor of the gas and taking that heat with it. This is kind of the same concept of a swamp cooler. So maybe you're probably familiar with this living in Phoenix, but a swamp cooler is basically a fan blowing over water. And in doing so, the water is kind of helping to get rid of the heat. Another property of water is this property known as pH. And pH is really a measure of hydrogen ions, or this H plus here, in a solution. And so if you look at this if you look at this chemical reaction here, you can see that in liquid water that the water is actually breaking up into what we call hydrogen ions and hydroxide ions. And so if you think about it, you've got your little Mickey Mouse, which has an oxygen and hydrogens. And so what happens is that the oxygen and one of the hydrogens hang out together, and then the other hydrogen breaks off on its own. And they actually kind of exchange, or I guess I should say that the hydroxide, which is this one here, it actually takes an electron with it, and so it has a negative charge to it. And so this is different from the partial negative charge. So we've got our complete water molecule, which has a partial negative and partial positive charges. And it actually dissociates or breaks down into the oxygen and the hydrogen. And this has a full negative charge. And then you've got your little hydrogen hanging out, and it's got a full positive charge. So this is different from the charges that result in hydrogen bonding. This actually forms something called a hydroxide ion. Now remember, an ion is just a charged particle. So we've got our negative charge there, and that's what makes it an ion. And then our little H plus is a hydrogen ion. And once again, the little plus sign is what makes it an ion. And we'll talk a little bit more about kind of pH and what this means, but this is actually what happens at a pH of 7. And so 7 is the neutral pH. And the only thing that is truly neutral is pure water. And that's because this reaction is happening at the pH 7. So the water is breaking down into the OH negative and the H positive. All right, now let's take a look. We're going to go over kind of the basics of what an acid is and what a base is, and then I'm going to draw out something that might kind of help you visualize it in another way. But first, let's take a look at kind of revisiting this pH 7, which is our neutral pH. So if you look at our pH scale down here, this is our pH scale. And you'll see that it goes from 0 to 14. And right at our 7 is our neutral pH. And remember, this is where that H2O is kind of breaking down into OH and H positive. And this reaction is reversible. So it's happening in both directions. So essentially, for every water molecule that breaks down into its ions, another set of ions is reforming back into water. So this is actually what's happening in your normal pure water. And so this is the water, like distilled water. You can drink it, it's totally fine. Now, anything that's on the lower end of the scale, so going from 7 down to 0, these are our acids. And the most acidic is at the end of the scale at around the 0 mark. And it becomes more and more acidic the closer you get to 0. So 1 is more acidic than 2. 2 is more acidic than 4, etc., etc. Now, anything above the 7, so from 7 to 14, we have our basic or our alkaline side of the scale. So this is also called the base or the basic kind of edge of the scale. And so those terms are used fairly interchangeably. And just like acid, the further away you get from 7, the stronger the base is. So the strongest base is actually up here by pH 14. So 13 is more basic than 12. 12 is more basic than 10, etc., etc. You can also kind of think of the strongest base as also being the weakest acid. So this is kind of a hard concept to grasp sometimes because we're always taught that you have acids and you have bases and then you have neutral. But this is really a scale. And so the closer you are to 0, the most acidic it is. And then as you move up the scale, you're just becoming less and less acidic. And so calling something basic or alkaline, you could also just call it a really weak acid. So I know that's kind of hard to wrap your head around, but that's another way to look at it. And if we look at kind of what this means to be acidic or basic, so let's go back up here to an acidic pH. So an acidic pH, it just means that the concentration of hydrogen ions is greater than the concentration of hydroxide ions. All right, and these little brackets, how we write the bracket with like a little H plus like this, the bracket means concentration of. So it's just kind of shorthand for saying concentration. So an acid is a situation where instead of having equal numbers of OH and H, now we've got more of the H. So more of that hydrogen. So hydrogen is increasing. On the basic end, you have less of that hydrogen. And that actually kind of ends up also meaning that you have more of that hydroxide. So these two, the hydrogen ions and hydroxide ions, are inversely related. So as one goes up, the other goes down. Going back to acidic pHs, so acidic molecules are going to dissociate in water and increase the hydrogen ion concentration. So that's what that means, hydrogen ion concentration. So the key thing with acids is that they increase the amount of hydrogen present. And if we look at, we can look at our example of hydrochloric acid here. And hydrochloric acid, the HCl, so this is a hydrogen atom and a chlorine atom. And when you mix them with water, it dissociates into hydrogen ions and chloride ions. And so since you've got more of this hydrogen going into that solution, it's making the solution more acidic. Some other examples of acids include these down here. So for example, for sulfuric acid, you can have hydrogen ions and these kind of sulfate ions that form. For acetic acid, so this is vinegar. Vinegar is really acidic, and you can see that hydrogen there. So once again, it's going to increase that amount of hydrogen ions. Ascorbic acid is just a kind of a fancier chemical way of saying vitamin C. And once again, it's got that hydrogen there, and so it's going to increase hydrogen ions when it's added to a solution. With basic molecules, when they mix with water, they increase the amount of hydroxide. So they increase OH negative, and that ultimately ends up in a decrease in hydrogen. So remember, these two are inversely related. So if you increase one, you have to decrease the other. So if we look at this example of sodium hydroxide, it's made up of a sodium atom and this OH. And so when you mix it with water, the NaOH dissociates into sodium ions and hydroxide ions. Some other examples of bases include things like magnesium hydroxide, and this is actually an over-the-counter kind of antacid medication called milk of magnesia. Also, things like bleach and soap are typically basic as well. So let's take another look at this kind of pH scale. So if we draw out our scale here, and we go from 0 to 14, and we've got our pH 7 right in the middle. Remember that 7 is the neutral pH, and really we can even say it's 7.0, because even if we look at 7.1, that's technically not neutral. It's actually a little basic. It's pretty close to neutral, but it's not actually neutral. And remember, the only thing that is truly neutral is pure water. And so at this pH of 7, the concentration of hydrogen ions is equal to the concentration of hydroxide ions. And that's because we have this two-way chemical reaction happening in which water is breaking down into hydrogen ions and hydroxide ions. But remember, this is a two-way reaction, and so for every time the forward reaction happens, the reverse reaction also happens. And so that's how we get our neutral pH. Now, on the side of the scale closer to 0, this is the typically what we consider the acidic side of the scale, or the more acidic. So pH of 0 is the most acidic. And then on the upper end, between the 7 and the 14, this is what we call the basic or alkaline part of the scale. But remember, we can also call the pH 14, we can say that it's the most basic or the most alkaline, but we can also call it the least acidic. All right, so if we look at a beaker of water right here, our pure water here, we've got our water inside, and so we've got our H plus and our OH negatives, and they're just breaking apart and then reforming water. Now, like I said, this reaction is going in both directions. And so if we kind of look back or link back to this idea right here, for every hydrogen we have a corresponding hydroxide. So we essentially have one molecule of water, and another water or molecule of water. Now, if we look at the same concept on the acidic side of the scale, so let's say we take our same beaker and we fill it with water. So we've got some hydrogen ions and hydroxide ions in there. But now let's say let's add some hydrochloric acid. So it's got a hydrogen and a chloride. And so this is hydrochloric acid here. And so what happens is when we add this hydrochloric acid into our beaker of water, it's going to break up into a hydrogen ion and a chloride ion. Now, for the sake of pH is really a measure of how much hydrogen there is in a solution. So it really has to do with the concentration of hydrogen. For the sake of our example here, we don't really care about this chlorine, and we're just going to ignore it. But if we look at our other substances there, we see that we have 3 H plus, but we only have 2 OH negative. And so in an acid, what happens is that you have a greater concentration of hydrogen ions than hydroxide ions. And so therefore, acids increase the amount of hydrogen in a solution. Now if we look at the basic or alkaline side of our scale, we'll take our beaker of water and we'll start out with just pure water in it. But now let's say we add a base, and so we're going to add our sodium hydroxide. This is called sodium hydroxide. And what happens when you add this to the beaker, it dissociates or breaks up into sodium ions and hydroxide ions. Now, just like with the acid where we kind of ignored the chlorine, because for the sake of pH, we really only care about the amount of hydrogen and hydroxide there is in a solution. So we're just going to ignore the sodium for now and take a look at the hydrogen ions and the hydroxide ions. And so now we've got 2 hydrogen ions and we have 3 hydroxide ions. So in a base, what happens is that the concentration of hydrogen ions is less than the concentration of hydroxide ions. So bases or alkalines, they increase the amount of OH negative in a solution, which also means that they decrease the relative concentration of hydrogen in the solution. The pH scale goes from 0 to 14, but it's not just a simple, straightforward scale. It's actually called a logarithmic scale. And what that means is that for every number change, there's actually a 10 times difference in the amount of, or the concentration of hydrogen relative to hydroxide. So basically what that means is that when you go from a pH of 7 to 6, there is a 10x difference between those two pH numbers. And so 6 is 10 times more acidic than 7. If we go from 6 to 5, 5 is 10 times more acidic than 6. And if we go from 5 to 4, 4 is 10 times more acidic than 5. And remember that we said that the basic side of the scale, we can also kind of think of that as just like a really weak acid. And so if we go from 12 to 11, there is a 10 times difference in the concentration of hydrogen relative to hydroxide there as well. And remember that the closer you are to 0, the more and more acidic you get. So 0 is the most acidic. The further away from 0 you get is the least acidic or the most basic. All right, so that's why we can say if we look at 3 and 2, so 2 is 10 times more acidic than 3. 3 is 10 times less acidic than 2. Now let's say we want to compare 7 and 5. Now you might be tempted to think that the difference in acidity between a pH of 7 and a pH of 5 is 20, meaning there's a 20 times difference in the amount of hydrogen present between those two numbers. But it's actually 100 times different. And I got that by taking 10 times 10. So I took this number times this number to get this number. Now if we look at a difference between 3, we have to take 10 times 10 times 10. And so we would get a difference of 1000x. So that means that something with a pH of 1 is 1,000 times more acidic than something with a pH of 4. So that's a big difference. And kind of an easy trick to figure this out is that for each number that you're changing, so let's say we want to go from 14 to 9, all right? So we've got 1, 2, 3, 4, 5. So to figure out the difference in acidity between a pH 9 and a pH 4, you just write the number 1, and then for each change you get, you're going to write a 0. So here we had a difference in 1, 2, 3, 4, 5. So we're going to write 1, 2, 3, 4, 5 zeros, which means that something with a pH of 9 is 100,000 times more acidic than something with a pH of 14. Now, every day, the pH of our environment is changing. So we eat acidic things. So think about things like pickles that are soaked in vinegar. That's really acidic. Soda and coffee is really acidic. You might eat some stuff that is basic as well. Now, we know that we need to maintain something called homeostasis. And with regards to homeostasis, that also refers to pH. So we have to maintain a relatively stable level of pH in order to survive. So once again, if we look at our kind of our graph of pH homeostasis, we have our set point right here in the middle. And then we have our acceptable range that we can survive in. So from there to there. And we can handle some fluctuations without a problem. But if our body fluids become too basic or too acidic, that is bad. So that's when you start having problems such as illness or even death. So it would be really bad if the pH of our body fluids change drastically really easily, because that would result in death. So you can kind of see that down here on this picture. So if we look at the normal pH of blood is between our 7.35 and 7.45. So this is what our normal pH of blood, and this is us being happy and healthy, and it means that our body is working properly. Now, we have these kind of substances and processes in our body called buffers. And a buffer is just something that helps to maintain our pH in this kind of normal homeostatic range here. Okay, so buffers do a pretty good job, regardless of how much acid or base we eat or drink. They do a pretty good job of keeping our body fluids within that normal pH range. Now, I'm not saying, it's not a good idea to go out and drink bleach, because that's going to cause problems. That's going to damage your esophagus and, could potentially kill you. But things that are actually considered edible, like lemonade and tomato juice, those things are really acidic, but our body can handle them usually thanks to these buffer systems that we have in our body. So for those of you that are moving on to anatomy and physiology in the future, you'll talk more about this bicarbonate buffer system in the blood. But basically, it's one key way that your body helps to maintain this normal kind of pH range is by adjusting how much carbon dioxide we are keeping in our body. So carbon dioxide it's a gas that our cells produce when we are making energy. And we typically think of it as a waste product, but we actually need some of it in our blood, because when carbon dioxide mixes with water, it forms an acid. And so this acid can actually dissociate into hydrogen ions and something called bicarbonate. And that can then dissociate into other hydrogen ions and carbonate. But the key takeaway point here is that when our body fluids become too acidic, we can actually exhale more carbon dioxide. So too acidic, exhale more. So this can increase our respiration rate. It can make us breathe deeper or exhale more deeply. By exhaling more, you're getting rid of more of that carbon dioxide. And as you're getting rid of carbon dioxide, your pH is going to, so we'll say here, decrease carbon dioxide. Your pH is going to increase and go from being acidic to basic, or at least closer to the basic end of the scale. If your body fluids are too basic or too alkaline, we can actually breathe more shallow. So we'll just say shallow breathing, where our breathing rate will decrease, we'll be breathing slower and we will not breathe as deeply. And in doing so, we can actually keep more of that carbon dioxide in our body fluids, which can help to bring our pH back down towards the acidic side of the scale. And so, if you think about it, when you're working out, your cells are processing a lot of energy. So when you're working out, you're producing a lot of carbon dioxide. So working out equals more CO2. And what happens when you're working out, you start breathing heavier and more rapidly. And that's because as your cells are producing more of this carbon dioxide, your pH is falling, meaning that it's becoming more acidic. And if it starts to get too acidic, it can actually lead to something called acidosis. And so one way that your body deals with that is by doing this. And you start to exhale more and you start to breathe deeper. Your respiration rate increases. And so the goal is to get rid of that extra carbon dioxide to bring your pH back up towards the normal level. Now, if your body fluids become kind of above the upper range, so above the 7.45, it's called alkalosis, and that's also bad. So you can see here that these are not good. These are a sign that your body is not maintaining homeostasis. It could be due to a problem with your respiratory system. It could be a problem with your kidneys. I didn't talk about it here, but your kidneys also help to get rid of hydrogen ions if you have too many, but it also your kidneys can retain hydrogen ions if you're becoming too basic. But coming back to acidosis and alkalosis, these are both bad, and they're a sign that there's something in your body that's not happening properly. So these are typically a medical issue that needs to be corrected. And if your pH levels get too far out of their homeostatic range, which is what we would see kind of up in this region here and down here, it will actually result in death. So it's really, really important to maintain that relatively normal pH. Now, like I said, these buffers do a really, really, a pretty good job of keeping our body in this homeostatic pH range. There's kind of a big trend right now for alkaline water. And so there's a lot of marketing out there to drink alkaline water because they claim that your body fluids are too acidic and they need to be more alkaline. But it's kind of funny because not too long ago, and it's actually probably still a trend, they used to say that you should drink apple cider vinegar, which is really, really acidic. So, apple cider. So it's kind of funny that, a couple of years ago they said, oh, you should drink apple cider vinegar. And I really should have flipped these two because alkaline water is more alkaline and apple cider vinegar is more acidic. But anyways, they say, oh, you should drink these things because it'll help you to kind of manage the pH of your body. But in reality, your respiratory system and your urinary system are already doing a pretty good job of that. So if you drink more alkaline water, it probably just means that you're going to pee out more of that alkalinity. So it means that your urine's going to be more alkaline, but that doesn't really affect your health. Same thing with apple cider vinegar. If you're ingesting more acidic stuff, it just means that your urine is probably going to be more acidic because your kidneys are going to be filtering out that extra acid. So as long as your kidneys and your lungs are working properly the way that they should, you probably don't need to be buying alkaline water or kind of, buying into this apple cider craze. If you think about humans have been around for, thousands and thousands of years, and our water hasn't always been alkaline or acidic. So probably just plain water is good enough.